So today I want to present the CheSS library that we are developing here, mainly at Barcelona Supercomputing Center, but we also have many other collaborators from various centers. And well, as Victor said, CheSS is a new library that will hopefully make it into ELSI. And so today I just want to present you kind of what CheSS is, what are it, how can it be applied, what are the performances, and so on. So I want to start with just a brief overview of the history and the motivation for the creation of CheSS. Then I want to talk about applicability, so it means what are the situations in which CheSS should be applied or will perform well. Then I will briefly show you the theory behind CheSS, and finally I will conclude with many performance data. So first, some history motivation. I mean, as Victor said, CheSS is a spin-off of the linear scaling version of BigDFT. In this code, we work with a localized set of basis functions, or we call it support functions. And obviously, this localized basis function lead to sparse matrices. And if we want to reach linear scaling for very big systems, we have to exploit the sparsity, obviously. And at that time when we were coding this package, we didn't find really a kind of a package that handles the sparse matrix routine in the way we want to have it. So finally, we just decided to write sparse matrix routines on ourselves within the BigDFT package. And then, this was working very well. And after some time, we thought, well, any DFT code that works with such a localized basis sets will have the same problem as we do. And so we decided to kind of isolate this sparse matrix routine from BigDFT to create a standalone library. And that we call CheSS, which stands for Chebyshev Sparse Solvers. And it's free. These libraries can be downloaded for free from this page here in Launchpad. And recently we have also, we wrote a paper that is currently in review and can be downloaded here from this archive link. So applicability of CheSS. There are many different solvers to solve these Kunshan problems. And what is the situation in which CheSS performs in particular well? I will show you later why, but I can already tell you now that CheSS performs extremely well for matrices that have a very small spectral width of the matrices. So this is basically the overlap matrix and the Hamiltonian matrix. And the question is, can we reach such small spectral width in practice? And here is a small test that I did with BigDFT, so the code that first uses CheSS. I have 5 different systems, so they are kind of here: DNA, pentacene, perovskite, silicon nanowire, or just water. They are rather big systems. Of course, you can see they are very sparse. And here on the left-hand side of the table, I show you the eigenvalues of the overlap matrix, so the minimal and maximum eigenvalue. You can see here the condition number of these matrices is extremely small. So, and if we have matrices with such a small condition number, CheSS is extremely performant in calculating, for instance, the inverse of this matrix. And the same also applies for the Hamiltonian. Here I show you the minimal maximum eigenvalue in electron volts. So you see the spectral width is order of 45, 50 electron volts, which is also quite small. And you can also see here, I noted also the Holm-Lummer gap. So all of these systems have a finite Holm-Lummer gap of a few electron volts. And I will also show you later that CheSS performs good if we have a large Holm-Lummer gap. So if you have metals, it still works, but it's not ideal. So I don't want to bore you with too much formula, just one slide with the basic equation. So the idea behind CheSS is to approximate a matrix function in terms of Chebyshev polynomials. So we have here the identity matrix, and these are the Chebyshev polynomials of order I. So you have to sum up until you get your desired degree. The matrix that enters this polynomial function here is such a scaled and shifted version of the original matrix M. And the expansion coefficients, I mean, can be calculated by this formula. This is textbook, so it may be complicated, but in practice it's very easy and it's very fast. So in the code you don't even see it, the calculations of these coefficients. What is the most expensive part is the calculations of the Chebyshev matrix polynomials. But here the nice thing about this is that they fulfill such a recursion relation. So if you calculate the polynomial of order j plus 1, you only have to know the polynomial of order j and j minus 1. Also, if you look at this equation here, you will notice that each column of the matrices are independent. So this means that it's very easy to parallelize because each column can be calculated independently. And only in the end, we have to perform a global reduction. And obviously, I mean, these matrices are sparse, but if you apply matrix to a multiplication matrix, you will lose this sparsity at some point because the matrix will get denser and denser. And to avoid this, we have to truncate these matrix multiplications here. And this is the key to get linear scaling. I mean, of course, because you have this truncation, you will introduce some small approximation, so you have a very small error. But usually, if this this cutoff is chosen in a good way, this error is negligible in practice. So, what are the functions that we can calculate at the moment? So, as I told you, chess has its origins in a DFT code. So, at the moment, we can calculate the functions that you need to perform a DFT calculation. So most importantly, it's a density matrix where the function here, I mean, this is the function that enters here in the calculation of the coefficients, is just the Fermi function. Or alternatively, we also use kind of an error function approach, since this usually, I mean, the error function decays faster to 0 and 1 away from the chemical potential. We can also calculate the energy density matrix. That's a very small modification. And we can also calculate matrix powers. And the important thing here, the exponent A can also be non-integer, so we can also calculate square roots, inverse square roots, and so on. And this is what we have at the moment, but it's very easy to generalize this to calculate other functions. The only thing that we have to change are the expansion coefficients. And within the code, this can be done within maybe 10 lines. It's really easy. The only requirement is that the function f that we want to calculate must be well representable by the Chebyshev polynomials over the entire eigenvalue spectrum. And this is the important point. That's why I told you in the beginning that it performs very well for matrices with small spectra. Because you can imagine if you have a very large eigenvalue spectrum and you have to approximate a function by these polynomials, you will then have very, very high degree, and the method becomes inefficient. I've already told you about sparsity. So chess can exploit sparsity in order to reach linear scaling. And in general, we have 3 different sparsity patterns. First of all, the one of the original matrix M, so that's the input that you give to chess. Then the sparsity pattern of the function that comes back from chess. In general, this sparsity pattern is slightly larger, since the matrix function kind of, in general, extends a little bit the content of M. And then we also have an auxiliary pattern that we need to perform the matrix multiplications. And at the moment, all of these 3 patterns must be defined by the user. I think this is well natural for the input matrix and also for the output matrix. This is something that chess doesn't know. I mean, the user must provide it. On the other hand, this auxiliary pattern here, at the moment, this is still something that must be provided by the user. We are kind of trying to figure out something more intelligent so that maybe chess can find a good auxiliary sparsity pattern on its own. But that's something for the future. So at the moment, all of them must be provided by the user. And typically, you just rely on the extent on your basis function or the distances between atoms to which this basis function belong. And here, I show you just in a cartoon, I mean, how it looks like. Here, we have the original matrix M. You can see that it's very, very sparse. And in gray, I indicated the sparsity pattern. So these are the entries that are 0. because there is no overlap between the basis functions. And if I then calculate, in this case it's the inverse, if I calculate without any constraints, so this is just with a cubic scaling Laplace, you can see that it's less sparse, this matrix, but still there is a lot of white, so there are a lot of zero here. And indeed, here this is the solution from CheSS, so you can see we use here a slightly larger sparsity pattern to kind of let the matrix extend from here to here. And it looks pretty similar. So here the white points are the gray points. So this means our sparsity pattern has been chosen correctly. And indeed here, I show you just the difference between these two plots on a different scale. So first of all, we can see, I mean, it's from 10 to minus 6 to 10 to minus 20. So all values here are extremely small. So this means, first of all, that our sparsity pattern was chosen correctly. So if we force the solution to be 0, it actually is very, very small. And secondly, it demonstrates that within the sparsity pattern, CheSS calculates the solution with a very high accuracy. And so if you were talking about accuracy, I will show you some benchmarks, but before starting, just kind of to remind you that there are two errors in CheSS. So first one is the error introduced to the sparsity pattern. So this is the truncation of these matrix multiplications that I was talking about. And the other error is just the Chebyshev fit by itself. And of course, then to account for this, we also have two definitions of the error. Or let's say first we have to define what is the exact solution that we should compare with. And the most straightforward approach is just to calculate the matrix function directly without any sparsity constraints, for instance with Laplace, and then crop it to the sparsity pattern. That's the most straightforward approach. The problem is that it usually violates this identity, right? If you calculate the matrix function and then apply the inverse function, we should get back the original matrix. But with this approach, this is usually not the case. And so therefore, the other possibility to define the exact solution is to calculate it directly within the sparsity pattern, and then to define the exact solution as the one which fulfills this identity here. And these are kind of the error definitions according to these two, accuracy measurements, according to these error sources. So the first one just measures the error introduced by the sparsity pattern. So this is the solution calculated within the pattern and the one without. And the second one is, in my opinion, more sensible, is this measure kind of the deviation from this essential identity, and gives you the accuracy of the Chebyshev fit itself. So I did a benchmark here, first of all, for the inverse. As a function of the condition number, here you see the relative error. And first, if you look at this error that measures the accuracy of the Chebyshev fit, we see here, this is this purple line. So it's basically down at 10 to the minus 10, 10 to the minus 11. So it's 0. So this means the Chebyshev fit is really exact within some numerical tolerance. On the other hand, if you look at the error that comes from the sparsity pattern, we see that it's slightly larger, so of the order of 10 to the minus 7 maybe, which is 4 orders of magnitude larger, but still in practice this is very small. So this means that the sparsity pattern that we chose to calculate the inverse was sensible. And the other important matrix function for DFT is the density matrix. And so here, to benchmark the accuracy, we were just looking at the energy. So this is the trace of the density matrix and the Hamiltonian matrix. And we see that we get a relative error compared to a correct result that we would get from diagonalization, a relative error of 0.01%. So this is in practice also negligible. We can also see it's interesting that we have a slightly larger error for a smaller spectral width, so this might be surprising. But the reason is very simple. If you have a small spectral width, then your eigenvalues are kind of more compressed, denser. And so then if you have a finite smearing that we apply in the Fermi function here, so the parameter beta here, this affects the accuracy a little bit more than if the eigenvalues are kind of more spread. But in any case, there is the order of 0.01%, so it's really very accurate. So after talking about accuracy now, some benchmarks, let's say, I told you that the goal of CheSS is to perform linear scaling calculations. And well, if you want to do so, you have to exploit the sparsity. So this means that the runtime, the calculation time, should only depend on the non-zero elements of your matrix and not on the total size of your matrix. And this is shown in this plot here. So I have on the x-axis the number of non-zero elements of the matrices, and you can see I have different matrix sizes. So I have matrix size 6,000 by 6,000 up to 36,000 times 36,000. But you can see here the runtime does not depend on the matrix size. It only depends on the number of non-zero elements. And it's a straight line, so it's linear. So it really shows that to calculate the inverse in this case, the computational effort only scales linearly with the number of non-zero elements, and in this way it will it's the key to it allows to perform linear scaling calculations. The other important point is about this spectral width, or in the case for the inverse, it's the condition number. As I told you, CheSS is extremely sensitive to this value. And indeed, you can see here, I benchmarked the calculation of the inverse for various condition numbers. So we start at about 2, 3, and go up to about 1 or 2,000. And you can see here, first of all, these dotted lines here. This is the polynomial degree that we need. It's on this axis. So for the smallest, for a small condition number, we have a degree which is sort of 50, 60, 70, maybe 100, depends. But then it explodes. So if you have a condition number of 1,000, we already are working with degrees of 2, 3, 4,000. And you can imagine this is not very efficient anymore. This also translates into the runtime. So first is these straight lines here. You can see for a small condition number, we're talking about a few seconds. And up here, we are already at the order of 10 minutes. And also you can see there are two different lines. So there's the purple line and the green line. And the only difference is that in this case, for the purple line, I was just telling CheSS start with a default guess for the condition number. As you might imagine, CheSS needs to figure out what's the condition number because it has to perform the Chebyshev fit over the entire spectrum. And in this case, I just told CheSS, well, start with the default guess, and then it has to find the correct value of the condition number on its own. And of course, this is very time consuming. And if I go to the green line here, I was let's say cheating a little bit. I was telling CheSS already what's the correct condition number. And you can see here you can gain almost 1 order of magnitude. But nevertheless, of course, this strong increase of the runtime as a function of the condition number remains. And the density matrix, the other important operation, of course, we have the same behavior with respect to the spectral width, so the smaller the better. But in this case, there's also another important parameter, and this is the homoluma gap. So, because you can imagine for the density matrix, we have to approximate a Fermi function. And if you have a small homoluma gap, this Fermi function becomes more or less like a step-like function. And it's very hard to approximate by polynomial, so we need a very, very large degree. And this is, you can see here, so I calculated the density kernel for various matrices with different gaps. So here we have a large gap of 1 eV, here we are going towards 0. And indeed, you can see the smaller the gap, the larger is the required polynomial degree. So these dotted lines here, you can see the larger the gap becomes, the more they go to 0. And also the difference between the blue, the yellow, and the orange is just the spectral width of the Hamiltonian. So no surprise, the larger the spectral width, the higher the polynomial degree. So to summarize, the worst case is a large spectral width with a small homolumo gap, and the best case is the opposite, so very small spectral width and a very large homolumo gap. Then parallel scaling, that's very important in chess. We, from the beginning, we designed chess to be a massively parallel library. And also the nice thing about chess is that the algorithm is intrinsically parallel. So the most time-consuming part is the calculation of the Chebyshev polynomials can be done independently, column by column. So in this way, we get a very, very good parallel performance. This is a benchmark for the calculation of the inverse. I did it with a hybrid one, so I used 16 OpenMP threads and just varied the number of MPI tasks. And you can see here that I start here at the order of, I think it was 80 cores, up to about 2,500, and I'm really very, very close to the perfect scaling. And this is also visible on the right-hand side here. I don't show the speed up, but the absolute runtime. So it's also very close to the ideal behavior. And you can see if I use many cores, it's possible to calculate the inverse of matrices of the order of a few 10,000 within a few seconds, which is quite good. We have also performed extreme scaling tests. I mean, if I go back here, you can see we are using maximally of the order of 2,500 cores, which is not bad, but we also wanted to see what happens if we go in larger. So here we went up to 16,000 cores, again for the calculation of the inverse. This time a matrix of 96,000 only, just this one. And you can see here, of course, if you are beyond, let's say, 5, 6, 7, 8,000 here, it becomes a bit flat, but nevertheless, also beyond 10,000 cores, you still get a decent speed up. And the matrix was not huge, so it was 96,000. If we had a bigger matrix, I think we could scale better here in this region here. And nevertheless, we are also trying to improve the scaling so that in the future we can kind of close this gap here and stay much longer close to this perfect scaling up here. And last but not least, we also benchmarked chess with other packages that are actually also in, let's say, or flavors of them are in ELSI. So for the inversion, for the matrix inversion, we compared chess with selected inversion that comes with the PEXI package, with ScalarPack and LayPack. And so I have here 5 different figures. So these are just 5 different matrices. So here it's 6,000, 12,000, 18,000, 24,000, and 30,000. Of course, all of them very, very sparse. And I did a test for various condition numbers. So first of all, if you look at the dense routine, so LayPack and ScalarPack, of course, there is no dependence on the condition number. And as you can see here, well, they explode as expected. And they are always the slowest method approach. So it becomes clear that we should explode the sparsity. And so now let's compare chess, which is the pink, the purple here, with the selected inversion. So as expected, the selected inversion shows no dependence on the condition number. So no matter what value we have, the runtime is always the same. And which is different to chess. You can see here, if you have a very small condition number of 2, so that's the case for big DFT, for instance, we are considerably faster than the selected inversion. But on the other hand, if we go to larger condition number, well, as I showed you previously, the runtime will explode, and there is some crossover with the selected inversion. For this, in this case, I would say to order of maybe 100, 200. So for matrices with a smaller condition number, it's usually better to use chess. If you have a condition number above this value, it's more efficient to use the selected inversion. And finally, this here we benchmark not the inversion but the density matrix. And I've shown you previously that LayPack and ScalarPack they perform very bad, so we didn't perform the benchmarks with these two approaches. just we compared two approaches which can exploit the sparsity, which is Chess and PEXI. So both PEXI is already in ELSI, Chess will introduce soon. And also we perform two different setups. So first of all, hybrid MPI OpenMP. So this means that we have both distributed and shared memory parallelism, and also an MPI only version. So we don't use a shared memory and only rely on MPI parallelism. So let's first of all, let's look at the hybrid version. So this is the purple and the green one. We see here in green the PEXI results independent of the spectral width, as expected, more or less. And in purple here, the Chess results. Again, for a small spectral width, we are considerably faster than PEXI. On the other hand, we again see this strong increase with the spectral width, but still for these values here, for this range, we are still faster. But then also we know that the PEXI, at least the version that we were using, doesn't have a OpenMP parallelization. So we are also looking at the MPI only version. So what do we see? First, if you look at Chess, we see this. So we have to compare the purple and the blue curve. We see that it becomes slower in all cases, even though we use the same number of cores. But if we use an MPI only version, Chess becomes slower, just because this design is better suited for this hybrid parallelization. On the other hand, if you look at PEXI, it's the opposite. So we go from the green curve to the yellow curve. So we see it becomes considerably faster. And so in here, even for the smallest matrix, there is a kind of an inversion of the order. So here, PEXI now becomes faster than Chess. And for the smaller matrix, well, Chess kind of recovers its advantage due to its linear scaling. But nevertheless, if you compare best effort, so this would be for Chess the hybrid version, the purple one, with the green, with the yellow one. For PEXI, we see that Chess is still more efficient. And with this figure here, I don't want to say that Chess is better than PEXI or the opposite. I think rather each package should be applied in a particular case. So Chess is very well suited for a small spectral width and large homo-lumo gap, whereas PEXI it doesn't suffer from this limitation. So PEXI can very well be applied also to large spectral width or small homo-lumo gap, so for metals, which we don't compare here. So I think if we have both in ELSI, that's a ideal case, then the user can choose what he wants. So if you have a small spectral width, he can go with Chess, or if he has a metal or a larger spectral width, well, then he chooses PEXI in this way, or he always gets the best out of the libraries. So I'm already at the end, the conclusion. So what is Chess? It's a flexible tool to calculate matrix functions. At the moment, we use it for DFT, but it can easily be extended to other purposes in the future. Then it exploits the sparsity of the matrices, and in this way reaches linear scaling. It works best for matrices with small spectral width, and in the case of the density matrix with large homo-lumo gaps. And it parallelizes very good. In particular, it has a very good OpenMP, that is shared memory parallelization. Most important point, that's why I'm talking to you right now, Chess is about to being interfaced by ELSI, so that we hope in the next release it will be completely integrated and is one of the supported library by ELSI. And that's it. I thank you very much for your kind attention.
Do we have any questions? Yes.
Yeah. Hi, Stephan. So this is Lee. A quick question. So, I mean, it's good that the Chess has both the MPI and the hybrid MPI OpenMP implementation, both of the versions available. But I think it's a little bit unfair to say that there is a PEXI hybrid MPI OpenMP version because we haven't released it yet. It's really a pure MPI only package. So yeah, so just in terms of labeling, I think the comparison is a bit unfair.
So, so do you think we should also compare with your latest hybrid version in that case?
I mean, we're working on a hybrid version, but I mean, the current packages that could be downloaded on the website. I mean, there isn't really a hybrid MPI OpenMP version. It doesn't exist. So
yeah. So okay. So I mean, yeah. So we should just compare best effort. Let's say.
CheSS is using 12 or whatever number of more cores, and Taxi isn't. Of course, I mean,
Just use the threaded
No,
blast.
yeah, using threaded blast.
I guess the hybrid chess implementation is using the same total number of cores. It's just using hybrid parallelism. 160 MPI times 12 versus 1920 MPI.
Yeah, I think what we're talking about is
No, it's just
I think just the green line.
The green line.
I don't know what that
green
means.
Yeah.
This one.
It doesn't
Shouldn't
exist.
be
So.
green line is just 160.
Yes, the green line is just one course. So that's it. So
I agree.
you can use the blast, but we observe that that's just doesn't help very much. If you want to do OpenMP, you have to do it at a much more sophisticated and fine-grainer.
I agree. Just if I may add one piece of information here, you can see that for these two matrices, there are no yellow and blue lines because here in the MPI only version, we run out of memory. So this kind of also forces you to use some kind of hybrid version, even if it's not implemented or not optimal.
Oh yeah,
so
very good because it gives us a good motivation to work on that.
Absolutely.
We are
Absolutely.
right now, but just as of right now, we don't have it.
Yeah, I agree.
Another thing is, could you go back a few slides before when you say the smaller spectral radius has a larger error? Yes, this one. So I guess you're comparing the density matrix obtained from a finite temperature calculation with the density matrix or energy compared obtained from diagonalization with a zero temperature.
This is correct. This is correct, yes.
I'm a little bit confused. Why not just compare finite temperature with a finite temperature? Don't add this extra explanation.
Well, yes. To be honest, I just when I did this plot, I was not paying well attention, so I compare kind of these two things which are not completely identical. In any case, I think for the if you have a large gap, I think it's natural to use zero temperature, but in chess I cannot because then the approximation doesn't work anymore.
Oh yeah.
So,
no, what I mean is for diagonalization, you have all the eigenvalues and other things. You just sum up with a different weight. Then you have energy defined at finite temperature. Then the error really might be even smaller, right? Than this 0.1%.
Yeah. No, in this plot, this is true. I'm comparing zero temperature with finite temperature. This is I agree. We should maybe redo this plot. I agree.
Okay.